the TNS. Then hand over the session to the speaker.
So we have particularly the faculty members. I'm not going to take much time. I will take a couple of minutes to introduce one last why we have. So, one last science forum is an organization that was founded in 1980. A few PhD students. So it has been grown in the state level organization now. So initially, the TNS was conducting lectures, all lectures within the campus of the university. The main idea is to get away and mark science in general. So now, after some time, what they bring felt is science, starting science within the persons who is involved in learning science, then go out of it and we communicate the science with the common man. That's how they come out of the college and basis and organize lectures. At some point, they start organizing the things together. We start from Chennai. So they go to the villages and take basic science concepts. Finally, come to Chennai and have a big festival of science. That's how we become popular. At the end of the Kashla, it was notified by the government of Tamil Nadu. Basically, the Senator job, and they asked us to get into the literacy program, total literacy program. It was a literacy program. They have been appointed as pushing the literacy program. The first people were telling me the 50 years, TNS was focusing more on literacy. In the meantime, TNS is remodeled and organizing 6 different verticals. They started with basic and second of science communication, and it also started as like propagation. Couple of magazines are published. One in Tamil, was started in 1987. Another one in English. The English is meant for college level students, and the community is for school level students. So, about the 2 magazines we have. From that, we have science books. So, we have publication groups separately. The third group is something else different development. So we have a lot of environment. All these things are developed by another group called the development group. And fourth group is working on provisioning science. We call it as the sum of equality. So there is a fourth group. That group is used in science. So there are 5, 6 groups we are working and we can cover a lot of science. Within science communication, I'm part of science communication. And every district we have a unit. And in this unit we have the science communication group. We felt that the students who are studying science in college not enough good understanding about the subject they are studying. So we have to go beyond the syllabus. The organization lecture that's how the PSL was started in 1980, 2018. The first lecture on participated very enthusiastic, and from that onwards, every year, every month, we are very good. And interestingly, we used to organize 3 lectures on Nobel Prizes. Every year, Nobel Prize will be announced, starting from the first Monday of October. But this year, first Monday was on 7th. The 7th is going to be there, the first Nobel Prize is going to be medicine and physiology. The second Nobel Prize is physics and chemistry, going to be economics, going to focus on physics and the other areas. So every year we organize 3 lectures immediately after we don't know when we get Nobel Prize. However, will be having one of these lectures on fall of line. And 26 we have another lecture which was one of the price of 2080. So the and then you will be the lecture. Third lecture. Guess who is going to be the number price? His name is not go beyond your syllabus and read the magazine. Please looking at this topic. This topic is practical. Breakthrough. Or is the probability. That's how we can think of it. We have a form, just click the form, we form it up, and put your evidence. Whoever is making the prediction more accurately, they will get good points. That's like
No, I know I don't do it. It's a lot of work, actually. Lots of emails. So difficult to.
The website is putting all which is and who is going to be the problem, probability. All these things are pretty much available. Let's go to the slide and get some idea who is working on that. I'm just making a so this is and today we're going to do that. Next time we will one and not going to planning you are
I remember head of the department, Dr. Amitabh Virmani, to felicitate our guests.
Thank you. Thank you. Hello, can you hear me well? Let me start by thanking the Tamil Nadu Science Forum and Madras Christian College for inviting me to give this lecture. Just 1 second, there is some problem with connecting to the Zoom. No. Yes, ma'am. Yes. Okay. Can you hear me well? Okay, so with this technical glitch sorted out, can you all hear me well? Okay, let me start with thanking college for inviting me for this lecture. It's the first time that I have come to this college, and the lecture hall is so big. It's the first time I'm giving a lecture in such a big lecture hall. So the title of my talk is, so I see that, but many of you must have seen this in the newspaper. Almost all newspaper ran this graph. So the aim of this lecture is to explain a few things about this graph, and you will see how they are related to black holes and gravitational waves. So February 11th, 2016 saw a very important day in general relativity. On this day, the first detection of gravitational waves was announced, and first direct observation of black hole binaries was announced, and first test of strong field, high velocity, nonlinear general relativity was announced. So these are very important developments. People have been trying to detect gravitational waves for a large number of years. The construction of the instrument was in progress for many years. Black hole binaries were discussed by Einstein himself in 1905, but the direct observation of black hole binaries was still very elusive. Solar system tests of general relativity have been widespread. There have been many weak field tests of general relativity, but strong field, high velocity, nonlinear test. Okay. Oh. The strong field nonlinear tests of general relativity are very rare, and the announcement of this event marked the beginning of this subject also. So these led to a new era, new era in many ways, new era in gravitational physics, new era in astrophysics, new era in computing, engineering, really many things. So in this talk, I will present the context of this discovery, the main ideas that go into this development, and also I will give you some idea about what the instrument did and what is the physics behind the gravitational waves and black holes. So the discovery is a big impetus for the subject of general relativity, which in itself is a crowning achievement of classical physics. And a lot of other things go into this discovery. In particular, there is a lot of math. Math is in general relativity, in coming up with the idea of how the waves will look like when two black holes collide. There is a lot of computation in conducting the simulation of how the two black holes merge. Then there is a lot of engineering in designing the instruments that detect these waves. So all these things combined led to a very interesting and very remarkable discovery. So the discovery was done by this instrument called LIGO. LIGO stands for Laser Interferometer Gravitational Observatory. So what this observatory saw, it saw the merger of two black holes. One black hole of mass 29 solar masses, and the other black hole of mass 26 solar masses. So these are very heavy black holes, and they collided with each other and produced a bigger black hole, bigger than these two, and a lot of energy was also thrown out in the process. And the energy that was thrown out is in the form of gravitational waves, and those gravitational waves is what this instrument saw, LIGO. So this event took place at a very large distance, at about 400 megaparsec, about 1 billion light years distance. And the signal that the LIGO detector saw was very bright. Was bright because both these black holes are above 25 solar masses. So both these black holes are larger than 25 solar masses. So the signal was very bright, and there was no doubt that this is a actual science event. So David Wrights of LIGO lab executive director, he did the announcement in his characteristic style. He said, "Ladies and gentlemen, we have detected gravitational waves." And this was after many years of work that these people had done. And they said, "Yes, we did it." And with the enthusiasm and with the excitement that they had been waiting to announce this discovery for many years, but it took a lot of time. Okay, so what goes into this discovery is the general relativity and black holes. So I thought I will give you some idea of what this is about. Um, I understand that many of you may not have done a course in general relativity and may not have studied black holes. So I will give a very broad introduction to this with pictures and no equations. Okay, so general relativity is a theory of gravity developed by Albert Einstein in 1915. In 1905, he developed the theory of special relativity. And then for 10 years, he was very the theory of special relativity and Newtonian gravity were not consistent with each other. In Newtonian gravity, there is no notion of time that the field takes to propagate from one place to another. The forces act instantaneously. I mean, when we say that the force between me and the earth is gmm over r squared, there is no reference to time. Like, it doesn't matter whether I am here or very far away, the force is always gmm over time, over r squared. There is no reference to time. So Einstein was very puzzled about this, and he thought very deeply about how Newton's theory of gravity can be made consistent with special relativity, and he came up with the idea of general relativity. In Newton's theory, gravity is a force that acts between two bodies. In Einstein's theory, the situation is very different. In Einstein's theory, what happens is that because of an object, the space-time around the object gets curved. So the gravity is manifested as a curvature of the space-time. So there is no as such concept of a force anymore, but curvature of the space-time itself manifests itself as an effect of gravity. So here is my attempt to explain how this is. So curvature of space-time. So here you see on the left, I have flat two-dimensional plane. If you draw parallel lines on this, they remain parallel, they never intersect. They always remain parallel. Okay, and here is a sphere. So a sphere is a curved space. On a curved space, if you start by drawing parallel lines, so let's say you shoot two lines at the equator towards the North Pole, they start to be parallel, but after some time, they cannot be parallel. I mean, they start to be parallel, but after some time they meet. So in that sense, they are no longer parallel, they meet. But when you started, they were perfectly parallel. So geometrical properties of space-time tell us that the space-time is curved. See, in this example, parallel lines never intersect on the left, but on the right, parallel lines do intersect on the sphere. So in this sense, the curvature of the space-time changes properties of how particles move or how things move. And this is what is manifested in Einstein's theory as gravitational force. So consider a similar situation now like this. So suppose there are two people who are like falling into this curved geometry. Then depending on the situation, how they are falling, where they are falling, the dynamics between the two can be very different. So for example, consider L2. So on N1 and L2 remain, like, if they are separated, they will remain separated for always, because these L1 and L2 lines do not meet each other. But on the other hand, if they start to fall on this L3 and L4 line, you see L3 and L4 lines, they come down and then they come together. Okay, so the fact that these things are coming together, you can think of this as some sort of force acting on them. But there is no actual force. This is happening because the space-time itself is curved. So how two things really fall can depend on in which space-time you fall. So depending on the curvature of the space-time, the forces felt by two particles can be very different in nature. So this is one effect, but there are many other effects. I mean, it's a big subject. So another effect is that the time for observers who are far away versus observers who are close to the curvature, they are very different. So in a different rates depending on in the surface of the earth ticks differently compared to the clock, which is very far surface. This is because of the Earth's gravity. These effects are actually taken into account in your phone, in your cell phone. In your cell phone, you have a GPS system, and GPS system regularly uses special relativity and general relativity to make appropriate corrections to tell you where exactly you are on Earth. Like it uses these satellites and bouncing rays and so on. And general relativistic corrections have to be taken into account. Otherwise, you will not know where exactly you are on the place of Earth. So all these effects are not just like theoretical curiosity, they have very, very practical applications. And in particular, in the GPS system, they are used very regularly. Okay, so black holes are the hallmark of general relativity. If the theory of general relativity is correct, then there is no escape from black holes. So black holes is a region of space-time where nothing can escape. It has a surface. So in this picture, I have tried to draw a cartoon. So it has a surface. The surface is, you can think of this, the edge of the black region in this diagram. The surface is called the event horizon, and this surface acts as a one-way membrane. So you can fall in, but you cannot come out of this surface. It's a one-way door or one-way membrane. You can think of it like this. And these are the you can think of these are places in our universe where the space-time is extremely distorted. So near the Earth, there is some curvature, there is some distortion in the space-time, but the distortion is not so much. If you don't relativistic correction in your GPS, you may get an error of 10 meters, but you will not get an error of 100 meters. Okay, but if you are near a black hole, important thing. So you have to really take all of these effects into account. The places where space-time is extremely distorted. And they exist in nature, there is no doubt about it. I will show you some pictures why we know that they exist. And they play a very important role in the evolution of stars and galaxies. Okay, so let us see how do black holes form. So most of the black hole in nature form due to collapse of stars. So suppose you have a very big star, it collapses and it becomes a black hole. So this process results in a black hole of a solar mass black hole, which is known as, which is of the mass range 3 to 100 solar masses. So here is a picture, like you have a star and it's under some pressure because of either its own gravity or it can be external pressure, or whichever way you compress this object sufficiently, then it will become a black hole. And in the context of gravity, the gravitational force itself acts as a pressure force that as a squeeze force that compresses such an object and makes it black hole. So we know about the solar black holes how by about which we do not know how they are formed. So in particular, there are these supermassive black holes which are at the center of almost every big galaxy. So Milky Way has millions and billions of mass of the sun, and we do not know exactly how they are formed. There is still no very good model for how these things are formed. We think that all these black holes start out small and then they grow big, but can they really grow this big is still not fully understood. So this is the general accepted theory that these black holes start small, and then grow large by eating nearby objects like nearby stars or nearby gas or possibly other black holes and so on. But it's not fully understood whether they can really grow this much. But we know that all these black holes exist in nature and we can see them. So here is a convincing evidence for why black holes exist and how do we see them. So consider the motion of stars around the center of the Milky Way. So this red dot is the center of the Milky Way, and these are the stars, like 5 stars that you see in this picture, these 5 stars. Now you look at these stars for a very large number of years. So you look at these stars for 10 years, 12 years. Then you will see that these stars move. Certainly every object in the universe moves in some way or the other. So they move, and they move in a very special way around some central object. So I will show you the video. So video of the star over the period of 10 years going around the center of the galaxy gives a very strong evidence that there is a central massive object at the center of the galaxy. And this is one of the strongest evidence for the black hole. For some reason, it has become so hot. Okay, so see, this is the motion of the stars. The five stars that I showed you, I'm showing the motion of these stars over a period of 10 years. So if you look at this motion, there is no doubt that these stars are moving around a central object, around this cross point, and the cross should be very heavy object around these objects these stars are moving. And this is one of the strongest evidence for existence of the black hole at the center of our galaxy. In fact, a Nobel Prize was given for this study a few years ago. Okay, so this is another picture. The picture is a little bit small, but the same orbits of the stars plotted over more number of years. So more stars and more number of years, and we see that there is a central object around which these stars are moving around. Okay, so when these objects move, they produce some sort of waves, like in electrodynamics. Many of you must have done a course in electrodynamics where you learned that if a charged particle accelerates, then it radiates. So here what is happening is that a gravitating body is accelerating because of the influence of another gravitating body, and as a result they produce some waves. So this leads us to the subject of gravitational waves, and I will show you a video of how these things come about. So see, so two objects which are just moving around each other, and just because they are moving around each other, there is a time-dependent gravitational field, and that give rise to all sorts of complicated waves. So I will play this one more time, just to give the impression of what this is. So you see two stars initially separated, they come close to each other and they start revolving around each other. In the process, some wave phenomena happen and waves come out, and then they merge, then even more waves come out. So this is the kind of event that LIGO saw in 2016. Okay, so what are these gravitational waves? So let me say very briefly about what these gravitational waves are. I mean, there is a very big theory behind it, lot of equations. That is not the topic here. So gravitational waves are fluctuations produced by moving masses with varying quadrupole moment. So the system that produces gravitational wave cannot be time independent. It should be time dependent, and time dependent, not any arbitrary time dependent would work. It should have a quadrupolar moment which is time dependent. Okay, quadrupolar moment time dependent. Then such an object will produce gravitational waves. So certainly if I shake my hands like this, my body has quadrupole moment and is changing in time, and that way I am producing some very weak gravitational waves. Or if two stars are coming close to each other, it has a varying quadrupole moment, so it is producing gravitational waves. So these waves all travel at the speed of light. They carry energy and momentum. They really carry energy and momentum. Like you can heat up your food with these gravitational waves. In the sense, I mean, if you can make a microwave out of this, you can actually heat up your food. So they do carry energy and momentum, but they are not easy to detect. They are not easy to use for heating your food because they are very weak. But once you detect them, there is an enormous science potential because what one can do with them, one can study the properties uh, of the sources where they came from, which you cannot study in any other way. So they have enormous science potential. So this is how modern science is. Like it's difficult to detect, but once you detect, you have a great potential. So you make a big instrument, and once the big instruments start to work, then you can do a lot of science with it. Okay, so let me say a few things about the sources. So as I was saying, if there are two stars which are orbiting each other, then it produces gravitational waves. So here is a cartoon picture. So here is a star which is going around another star in some complicated orbit. And when they go in this orbit, then they produce these gravitational waves, like these arrows, these light purple lines that you see. These are the representation of gravitational waves. Now, it so happens that in many of these systems have a natural clock with them. So if one of these objects happen to be a pulsar, then this pulsar will tell us the precise rate at which the gravitational energy is coming out of the system. And that will reflect in the change in the timing of this pulsar. And in fact, this was one of the first indirect discovery of gravitational waves, where one such system was found. It has a name. It's called Hull-Taylor pulsar system. And in this system, some gravitational waves come out, and as a result, the time period of the pulsar changes a little bit, and the one can observe this timing is changing, and it perfectly matches with the hypothesis that the system is radiating gravitational energy. How do gravitational wave look like? So here is a picture. So if a gravitational wave comes on and a gravitational wave comes on these rings of particles, then how does it changes the properties of these particles? So you see, this is what happens. So a gravitational wave comes on. So suppose you have a bunch of particles, and a gravitational wave comes. Then what happens is that because these are fluctuations in space and time, the ring of particle gets deformed. And the deformation is roughly of this type because they are wave-like, so it gets deforms in this way. Okay, all of you got some idea of how this is? Okay, so now I will show you there are two types of gravitational waves. One with the causes the deformation in one way, and the other that causes the deformation in another way. Okay, so let's see if you can see this. So there is one set of gravitational wave which cause this longitudinal and vertical deformation, and the other one is this cross deformation. So it shows both. See, one is called the cross polarization, which is causing the deformation in the cross direction. The other one is circular polarization, which is roughly causing the circular polarization, circular deformation. See, so this is some general phenomena of how the gravitational waves will deform this picture of Einstein. And if there is a cross polarization, then it will deform one way this way and then next way this way. And if there is a circular polarization, then it will deform this as if the particles are going in a little circle around the direction in which gravitational wave is coming. Okay, so what all this has to do with India, and what can we say? What can we do with this science? Okay, so India is a leader in this subject. India has very many people working in LIGO, and they have made very important contribution to the subject. In fact, there is a program for LIGO India, and our Prime Minister himself went to the US when this program was approved and announced, and the funding for this program has been fully given now, and now we are just waiting for this instrument to be ready. So what is LIGO, and what is LIGO India, and where do we stand with this program? So LIGO is a very sophisticated instrument. It has long interferometer arms. So what it does is that it runs some lasers in 4-kilometer length arms. These are very high power laser, very high quality lasers. And this is an extraordinary effort to avoid, so when these gravitational waves come, then these masses move in certain way. So what we want to study is to study the motion of these masses because of the gravitational wave, and we want to get rid of all the other motions of these masses. So it requires a very systematic and very extraordinary effort to avoid forces on the test masses to reach the sensitivity that you need. Sensitivity to test the motion of these masses because of the passage of gravitational wave. This leads to a fractional change. A passage of the gravitational wave roughly corresponds to a fractional change in the length of these arms, which is 10 to the minus 21. So you see, 10 to the minus 21 is a very small number and it's difficult to detect. And LIGO instrument, the way it does this is that it measures on this northwest corner of the USA in a city called Hanford, and it does a similar measurement in the southeast corner of the USA in the city called Livingston. And this is how the two detectors look. So this is the detector in Livingston, Louisiana, and this is the detector in Hanford, Washington. So these are very old pictures. Just to emphasize that the detectors are actually in making for many, many years. Okay, so just to show you how this whole thing works. So here is the animation. So here I am showing the two arms of the interferometer, and this is a very high quality laser. So this laser comes and it splits into two parts, and it goes into this long tubes and comes back. When it comes back, there is a perfect phase matching. Okay, because the lengths are exactly 4 kilometers, there is a perfect phase matching. So there is no light. You see what is called destructive interference. Okay, but if the length of these arms change a little bit, so you see, as the gravitational wave passes, the length of these arms changes a little bit. As the lengths change, you see the light comes here. See, as the length of these arms are changing a little bit, from destructive, the interference changes to constructive, and you see this light. Okay, so I'm sure all of you must have studied the process of interference in your optics course, and this is a very interesting illustration of how the phase shift because of the passage of gravitational waves, you see the interference. So let me play this once again without speaking, so you can understand what is happening. Let me see. Yeah. See, perfect destructive interference. And now the gravitational wave passes. So the lengths of these arms change a little bit. And as the lengths of these arms change, there is a constructive interference, and you can see the light at this end, at this detector. You see how this is how the detection of gravitational waves is done in practice. Okay, so there is a global network of these detectors. There is a detector in Hanford, Louisiana. There is a detector in there is a detector in Washington. There is a detector in Louisiana, and uh, and there is a plant detector in LIGO India, and there are two detectors in Europe, Geo and Virgo, and there is a detector in Japan called Kagra. So there is a global network of detectors which uh, do these observations all at the same time, you can say. Okay, so you might say, okay, so we already have so many detectors. Why do we need LIGO India? What is I mean, we are spending so much money on constructing this detector. Why do we need this? Okay, so LIGO India is very, very important and it's a unique detector, and we really need this detector for the following reason. So uh, the two detectors in the US, they can only tell you the location of the object via this graph. So if you want to know a gravitational wave came from where in the sky it came, you cannot pinpoint precisely in the sky where the wave came from. Only you can tell with this much accuracy. But if you have LIGO India, three detectors working at the same time, then your precision increases manifold. So from the two detectors in the US versus three detectors, including the one in India, you can tell where exactly the gravitational wave came from with a high precision in the sky. So LIGO India is a project which houses infrastructure to house build detector, which LIGO experiment will provide. It will help us in locating the sources. It will help us in determining the polarization of these waves, whether they are circularly polarized or cross polarized or some linear combination of them. And of course, if the three detectors are running, then you will have greater detector uptime. You can do the observation for many more hours, many more months, and that way you can discover many more gravitational waves. Okay, so now let me just say a few things about the discovery itself, the place where I started the talk in 2016. The discovery was announced in this technical paper. This paper is published in Physical Review Letters on 20th February 2016, and not 12th February 2016. And not just one paper came out in this journal on that day, many other papers came out, and a lot of them were related to gravitational waves and gravitational wave physics. Okay, I will not bother to you with the details of this. Okay, so this is what the instrument saw. So as the gravitational wave came, from the interference pattern, you can figure out how the arms of these detectors move. And this is how the arms of the detector in Hanford moved. So this is the noise that the detector in Hanford saw, a signal that the detector in Hanford saw. And the signal is in very good uh, agreement with the theoretical modeling of a similar signal that you can do using numerical relativity. So as I was saying earlier, a lot goes into this analysis, in particular computation and numerical relativity goes into this. So what one can do is that based on numerical relativity, one can attempt to draw the expected nature of signal in such an instrument. And this is what you expect. And you see it matches very nicely with the observation that was made at Hanford. If you subtract the expected signal from the observed signal, then you only see noise. So this is the residual signal. And a lot of analysis has been done on if there is any physics in this residual noise. There is no, it's actually a noise. Another interesting thing is that the distance between Hanford and Livingston is such that it takes time for a gravitational wave to travel from Hanford to Livingston. So if one takes into account that time, and shifts the signal by exactly the time it takes, then the signal at Livingston matched with the signal at Hanford. So this is the signal that was seen at Livingston, the blue one, and the orange one is the shifted version of the Hanford signal. And you see they very nicely match with each other. So if you subtract the Livingston signal from the numerical modeling, then again you see only noise. You do not see any signal left in this. So this is a set of graphs which are published in many newspapers. They were everywhere in 2016. I'm sure the older people must have seen this in the newspapers. And it really highlights and shows how important and how difficult this discovery was. Okay, but all this was 8 years ago, and we are still coming to terms with all this because there is so much excitement and so much new physics that has come out of this development. Um, but for a younger person, the question is, what is the future of all this? So the future of this subject is actually very bright. And India especially needs a lot of young people to work on this subject because the LIGO India is not yet ready. We need a lot of engineering support, a lot of science support, a lot of manpower to do all sorts of analysis for the LIGO India project. The future in the bigger scheme of things is a project called LISA. So this stands for Laser Interferometer Space Antenna. So the idea here is that instead of having these detectors on the Earth, we will have these detectors in the sky. So in the sky, there will be 3 satellites, and these satellites will shoot lasers between them. And if a gravitational wave passes, the distance between these satellites will change. And by measuring those changes, we can try to figure out whether the gravitational wave has passed or has not passed. So LISA is a space-based gravitational wave observatory building on the success of a project that was done a few years ago called LISA Pathfinder. This is led by European Space Agency. And it's a mission that is in collaboration with the European Space Agency, NASA, and International Consortium of Scientists. So this is how roughly the satellites will look like. So as I said, 3 satellites will go around the Earth and they will shoot lasers between them. And if a gravitational wave passes, the distance between these satellites would change very slightly. And that slight measurement is what we are after, and that will tell us whether the gravitational wave has passed or not. So this is a picture of a cartoon picture of how these lasers and the satellites would work. So LISA is really very important. It will open the low frequency gravitational waves uh, uh, possibilities, because right now we are limited by the amount of length we can have. So right now the length of the detector is 4 kilometers. We cannot make it 40 kilometers. It is just not possible. Because at the 40 kilometers, the curvature of the Earth will come into play. The earthquakes on the Earth will come into play. There will be trucks passing in a 40-kilometer stretch. So there will be vibrations because of that. So 40 kilometers is just undoable. 4 kilometers was very difficult. But if you go in this space, then you can do as much as you want. And one can make an arm which is 2.5 million kilometers. And you can shoot lasers from one place to another, which are running for 2.5 million kilometers. So this is really very remarkable thing. And the technology has been shown that it works. So it will be very good to have this project running. So the LISA will do many things. It will trace the origin and growth of the mergers of the supermassive black holes. So this is what I said earlier. We understand how the small black hole forms, but we do not still fully understand how the big black holes form. But if we have LISA, then we will be able to study how the mergers of supermassive black holes happen and how the origin and the growth of these black holes happen. We can do some sort of cosmology with them, because not only it will see the low frequency gravitational waves coming from astrophysical event, one can also study the low frequency gravitational wave coming from cosmological events. So one can study the nature of the rate of the expansion of the universe. Nature of cosmological physics we can study from this. We can explore fundamental nature of gravity and black holes via LISA, and this is perhaps a technical point. We can also study what is called relic gravitational waves. Like if in the past there were some black holes which were colliding, then if there is a gravitational wave produced by such collisions, where are these gravitational waves? So even those questions we can address and answer. Okay, so let me just end my talk with this last couple of slides. So we have come a very long way in our understanding of gravitational waves and black holes. Subject started in 1905, and in the last 100, 110, 120 years, the subject has seen enormous progress. Very good physics understanding have come out of all of this. But still, there are many unanswered questions, many unanswered theoretical questions, technical questions, numerical questions, engineering issues, technical issues. There are many, many unanswered things. So for all this, I mean, we need people to do research on such topics. Gravitational waves opens a new window into the universe, where we can study the universe by looking at gravitational waves, how they are produced, the nature of the signal, the nature of the waves, and so on. LIGO India will come up in few years, and it will help in locating gravitational wave sources in the sky. That will be a very big achievement. LISA will help us understand other mysteries of the universe. So given this, the subject is, the future of the subject is very, very bright. So with this, I will end, and I'm happy to take questions.
Anyone is having something, please raise your hand and come to your page and our the mic. Yes, it's under live telecast. So we have two mics. One is going to the Zoom, other one is going to the YouTube. So please raise your hand to ask the question.
So what do you think about the gravity?
Yes, I think you are referring to the particular. Yeah. So just to put things in context. So photons, there is something called wave-particle duality. Every particle can be also viewed as a wave, and every wave can be viewed as a particle. The same physics applies to gravitational waves. But when you do wave-particle duality, the quantum mechanics come into the picture. What I presented in this talk is all about classical physics. So indeed, there has been discussion on what is the wave, what is the particle nature of the of gravitational waves. In fact, there is a name for this such particles. It's called a graviton, and people do study, for example. Yeah. So yeah. So graviton. If you take graviton, the question is not that it exists. I mean, graviton. Yeah, quantum mechanics.
Thank you.
Yeah.
Next.
What is this?
Two mics.
Oh, okay. So should I speak in this one?
Yeah. One is for YouTube, one is for theory.
Okay. So my question is, you were talking about detecting gravitational waves, right? And you said that we can know things about the sources which produce those waves.
Yeah.
So can you tell us more about what kind of information you get from the waves?
Yeah. Yeah. Thank you. So perhaps the best figure is to show is this one. So you see, the signal that we get from this black hole merger, there is a precise profile that you get. Like it has a very specific time dependence that it goes like this, and then it becomes louder, and then it becomes quieter. So there is a lot of information hidden in the way it undulates, in the frequency of these oscillations, in the amplitude, in the time scale it takes. So all that is the physics information which we can extract. Yeah. So from this graph, we can extract the properties of the black holes that collided, like the masses of the black hole, how long it took for them to collide, and things like this.
So as we use string theory for a huge part of gravitational physics and black hole, do you think string theory is actually valid for it? Like string theory is actually valid for explaining gravitation? So is string theory actually valid for explaining gravitation and black holes?
Okay, so I think the question is string theory right in discussing properties of black holes? Is that the question?
Yes, mathematicians don't agree on it, but physicists do.
Okay, well, I work on string theory, so I will give you my perspective. So what I presented in this talk, this is all classical physics. So classical physics is general relativity, and there is no dispute about whatever I said in the talk has been experimentally observed or tested. There have been all sorts of tests of general relativity. But if you ask more difficult questions, like questions related to quantum mechanics, what do we mean by the entropy of black hole, or what do we mean by what is inside the black hole, something of that type. So those questions cannot be addressed within the framework of general relativity, because general relativity will just give you some classical picture. So for that, you need some deeper theory, more complete theory, and string theory is one such theory. And string theory has many successes with black holes. For example, for a special class of black holes, which have very different properties than the black holes that we see in the sky, zero temperature, have some supersymmetry and so on. For such black holes, one can exactly count the number of microstates such a black hole will have. And that is regarded as one of the biggest successes of string theory. So in some sense, string theory has a lot of success with black holes. But then there are many other questions which string theory also cannot address. And as you said, there are other controversies around it. So this is the summary.
So I have sort of a paper of black rings. I was wondering if it's like a black hole of so like how describe black holes with the technologies and how that works.
Okay, thank you. Yeah, so during my PhD, I worked on this project called Stability of Black Rings. Maybe that's the paper you saw. So the situation is like this, that if we work only in 3+1 dimensions, like in our normal world, then one can prove that there cannot be anything other than spherical black holes. So this was proven by Hawking many years ago, called Hawking topology theorem, that only the spherical black holes are possible. But then somebody was asking about string theory. So with motivation from string theory, people in the late 90s, you can say in 95 onwards, 1995 onwards, people started studying general relativity in different dimensions. How general relativity would behave in 5, 6, 7, 8, 9 dimensions and so on. I mean, this question, many people find it very interesting, many people find it boring. Interesting because there is a lot of richness in higher dimensions. Boring because we don't live in higher dimensions, we live in 4 dimensions. So depending on where you come from, you may find this interesting or boring. During my PhD, I found this subject very interesting. And Amparan and Rial, who discovered a black hole which had a ring-like topology in 5 dimensions. So there is a circle, and the cross-section of the circle is a sphere. So S1 times S2. So you cannot picture this in normal normal three-dimensional space because it's a complicated topology. But this is the kind of black hole they discovered, S1 times S2 topology. And I worked on that subject. And from then onwards, it has been very clear that black holes with different topology are possible in different dimensions. So in 5, this is one possibility. In 6, there are other possibilities, and so on.
So what do you think, like, how would, like, some of the more modern properties of black holes, of like Hawking radiation would change in dimension, because particles in different dimensions behave differently? Would that change the property of black holes? Or
No. So another very important thing about black holes is that they are very universal. All properties of black holes are universal. Not all, many properties are universal. For example, the horizon being a one-way membrane, this applies to all dimensions to all black holes. The fact that black holes Hawking radiate, they radiate quantum mechanically at some temperature, that applies to all black holes. So there are many properties of black holes which are universal, but then there are some properties which are not so universal, like the topology of the event horizon. So to answer your question, the particle emission because of Hawking radiation, that applies to all black holes without fail.
okay, thank you so much. One last question would be, you talked about LISA as a project, and I was wondering, like more than supermassive black holes, I was interested in the black holes that were, during the formation of the universe, the primordial black holes, which are not exactly the biggest black holes we have seen. So I was like wondering how can possibilities help with the like prehistoric black holes.
Yeah, so I did say a little bit about this, but this was a technical point I was making, these relic gravitational waves. So as you said, there are many models which discuss what would happen if there were small black holes in the very past of our current universe. So if we go way back in the past, suppose there were small black holes and they collide and form something, primordial black holes they are called. So whatever, this is a theory, it's under some debate, but whatever happens, they will produce, if two black holes collide, they will produce classical gravitational waves, which will be sort of relics and they will be everywhere. So the question is, by LISA, can we observe such gravitational waves? And if we can, then can we say something about the abundance of primordial black holes or some other properties of density of primordial black holes or something of that type? So this is a possibility. Okay, I'm happy to take as many questions. I have a lot of time.
For my question is, does gravitational waves affect dark matter specifically?
Do they affect dark matter?
Yes.
Thank you. It's a very interesting question. Nobody knows what exactly is dark matter. So too many thoughts are coming to my mind. But let me just say in the following way. If dark matter is actually a particle kind of matter, which we do not see, and if it interacts with gravity in the same way other particles do, then gravitational waves will certainly affect dark matter. In exactly the same way they affect electrons, in exactly the same way they affect the particles in my body and things like those. So if dark matter is actually a particle concept, then I would expect that gravitational waves interact with them in exactly the same way as it interacts with other particles. But if dark matter is some other theoretical concept, like some modification of gravity or some new term in Einstein's theory of relativity, something of that type, then of course things will be different. Then one has to understand what do we mean by interaction of gravitational waves with dark matter. Then the question itself has to be rephrased and thought in a different way.
Sir, does gravitational density would affect the gravitational waves indirectly?
Sorry, I did not hear properly. Can you please say it again?
Does gravitational lensing
Lensing.
Ah,
Yeah.
yeah. Could affect the gravitational waves indirectly?
Yeah. Okay. So I hope many of you have done a course in optics where you study diffraction, some basic diffraction. Have you guys studied? No? Okay. If you have studied, that's very good. If you have not studied, then let me just say it this way. Gravitational lensing is nothing but diffraction of waves. So there is some material in front of you and you are sending some wave, and this wave will deflect because of this material. Okay, exactly the same way when you throw a laser light into a hole, the light on the other side of the hole is some different pattern. So exactly the same thing will happen. If you throw a gravitational wave on some material, it will scatter in some way, and that scattering is what causes gravitational lensing. One can write down equations and make it more precise, but essentially this is the idea. So there is really no difference between gravitational lensing, scattering, and diffraction. So it does happen for all waves, and it happens for gravitational waves also. Yeah.
How were gravitational waves first detect, and what instrument are used to detect waves?
When they were first detected and what instruments were used. Yeah. So this is how I started my talk. So they were detected, they were announced on February 11, 2016. And this was the first direct detection of gravitational wave. Indirectly, they were known in this model. This is called Hull-Steller binary pulsar. In this model, they were known indirectly, but directly they were first announced in 2016. Yeah, and LIGO was the instrument that discovered this.
Thanks.
Yeah, in the back.
So I have this question from childhood. Why do you think gravity exists?
Why do you think gravity exists?
And how does it exist?
Why do we exist? God made us. So no, I mean this is how the universe is. I don't think there is a more useful answer to this. Uh, in the universe that we live, there is a phenomena of gravity, and we study that phenomena. I think that's the only. I mean, there can be another universe in which gravitational forces are weaker or stronger, or electromagnetic forces are weaker or stronger. All such possibilities are possible, but in the universe that we live, we see that there is a phenomena of gravity, and it is described by this Einstein's theory of relativity.
So if there is no question. So if there is no question, can we go ahead and wind up the session? Okay. Just a final question.
Sir, how these detection of gravitational waves help in finding the particle matter of the gravitation, like gravitational?
You are asking how the detection is telling us about how the detection is telling about the particle nature of the. No, actually, in these instruments, we only test the wave nature of the waves. We trust quantum mechanics so much that from there we can infer that it has some particle nature. In particular, what we can do is that we can construct these waveforms by scattering of gravitons. So this calculation can be done. You consider like bunch of particles which scatter with each other, and you ask how much gravitational wave is produced in this process. So that is a quantum mechanical scattering process, and the profile of the waves that you get matches with the classical profile. So there is no direct inference you can draw from the experiments themselves, but indirectly you can confirm whether this idea of whether graviton idea is correct or not. This you can confirm via this calculation. So this has been done.
Okay, so our last item is the vote of thanks. Do you have a question? Welcome.
Sir, can you explain about the Hawking radiation?
Yes, I can say very briefly what this is. So, as I said, classically, black holes is a one-way membrane. Everything that falls towards the horizon goes inside the horizon and can never come out. Okay, so it's an object which you can say like a perfect black body, like black body you study in your class 12. So black body is an object which is black, radiates nothing. So this is a perfect black body in that sense. Okay, but then this is classical physics. What Hawking did is that Hawking considered quantum mechanical particle in the presence of black holes. So you consider doing quantum mechanics in the presence of black hole, and then what he found is that this picture of exact black body is not perfectly correct. It is a black body, but not at zero temperature, but at a finite temperature. And that temperature is called the Hawking temperature. So black holes are perfect black bodies at some finite temperature, and at that temperature they radiate particles. So that radiation is called Hawking radiation.
Okay, so Aditya Verma will give the vote of thanks.
So before going to my duty to say the vote of thanks to a couple of announcements. So are you aware that Tamil Nadu Science Forum has come up with a competition for predicting the Nobel Prize winners for 2024? Next week is going to be announced. You can participate, come to know what are the areas of they are considering. We have sent the Google form link as well as some reference to a site called Climate. This agency is an analytical agency which based on the citations world over for various scientists, they are predicting the Nobel Prize winners every year. They are doing it from 2002 onwards. So they may not get on the same year, but 20% they are claiming that they have got this. So you just go through the site, it's a helping hand. No, we are not restricting you to only see that site, but I found it very, you will get a fairly well exposure of what is happening in the scientific world, the cutting edge research areas in physics, in all the subjects, physics. So this competition is only for physics, chemistry, and physiology and medicine. So if you I have sent the link to the department, please read the request to supply to all the students. If any of you have not received, please let me know. Right here, you can get me that. Okay, so with this, a profound thanks to Professor. Lot of questions will be there in your mind. He patiently answered all your questions. Of course, there will be a lot of questions. You have to pursue these questions and come to it. That is your future in physics. So after physics, what is there? Metaphysics, philosophy. So I found some questions are spilling over to metaphysics. You asked some philosophical questions. Okay. So with this, I thank you very much on behalf of Tamil Nadu Science Forum. We thank Madras Christian College for organizing this this lecture this evening. Thank you very much. And on behalf of Tamil Nadu Science Forum and Madras Christian College, give a big applause to Professor Virmani. And last, not the least, all of you come in very large number. We are very happy about. Thank you.